In this lecture, we will study what is called spectral graph theory. It means the analysis of the spectrum of a graph, or in a very generic term, what we mean is a systematic study of the eigenvalues and eigenvectors of the adjacency matrix or the Laplacian matrix of a graph. So, you all know what is an adjacency matrix, how you can represent a graph in form of its adjacency matrix. There are certain transformations that you can do on the adjacency matrix to get some other matrices. One of these very standard transformation is known as the Laplace transformation. So, by doing that we get Laplacian of the graph. Do not confuse it with the Laplace transformation that you study in algebra. It is of the same spirit, but of course, different. If you do the mathematics, it looks slightly different. So, why we should study the eigenvalues and eigenvectors of a graph? This is the first question that we need to answer. And I think yesterday you had a very good introduction to PageRank, what we call the PageRank algorithm, or which is also known as the eigenvector centrality. It is actually the principal eigenvector of the graph, that is the eigenvector corresponding to the highest eigenvalue of a particular matrix that we kind of defined. We called it AL. Remember, it is not exactly the adjacency matrix, because we divided each of the elements in the rows by a factor which is the degree of that particular node representing that row, and we also multiplied by a damping factor, that is W in the diagonal and 1 minus W to all the other things. So, we did some kind of a transformation. It is not exactly a Laplacian of the adjacency matrix, but in Laplacian you do something similar. So, this is just one of the things which the eigenvectors can tell you. There are a whole lot of other very interesting properties of graphs or networks, which you can get an idea about from its eigenvectors and eigenvalues. And this whole field is known as spectral graph theory. Sometimes it is also called algebraic graph theory. And as you can see, it involves a whole lot of linear algebra. You take the adjacency matrix and do a lot of tricks using linear algebra tools, and you find out properties of large graphs. So, we will see some of these in course of this and the next lecture. So, the first question is, why do we call it spectral graph theory? Essentially, there should be some spectrum. You all might have heard of the spectrum of a speech wave, right? So, if you talk of a speech signal, you can look at the signal from the time domain, then you will look a curve like this, or you can look at the frequency spectrum, where it tells you for each frequency what is the corresponding kind of energy that is in the for that particular wave, that what energy per frequency is delivered. So, that is the spectrum. So, you are moving from time domain to frequency domain. Similarly, here is a shift from the normal node and edge representation of the graph to some other representation. And what is that representation? Here the representation is regarding the eigenvalues. So, what you do is you compute the eigenvalues of the adjacency matrix. Okay. Let me also mention at this point, I talked about the Laplacian. You could also use the Laplacian, or for that matter any other transformation on the adjacency matrix, but for this lecture we will only consider the adjacency matrix and its spectrum, because you all know what is an adjacency matrix, and I think that is the simplest to understand. Now, you take the adjacency matrix A of a graph and compute its eigenvalues, and let the eigenvalues be lambda 1, lambda 2 up to lambda n. So, then n is the number of nodes in the graph. You know that if a graph has n nodes, then it will have n eigenvalues, because the adjacency matrix A has dimension n cross n. And we also enforce that lambda 1 is greater than equal to lambda 2 is greater than equal to lambda n, so on. Now, why such a relationship exists? Such a relationship will exist under certain conditions, right. First is that all of these lambda n's should be positive, should be real numbers and not complex numbers. If they are complex numbers, it is difficult to compare it in this way. It turns out for graphs, the adjacency matrix has certain properties for which all the lambdas are actually real. So, you get real valued eigenvalues. So, you can order them, and the largest eigenvalue, which is the lambda 1, is called the principal eigenvalue, and then the others are ordered. Now, when you have computed all the eigenvalues, then you can get the spectrum of the graph. The spectrum of the graph is basically the plot of the eigenvalues with their corresponding multiplicities. What is a multiplicity of an eigenvalue? So, suppose there is an eigenvalue 5 for a graph, but 3 of the eigenvalues are 5. So, you have 3 eigenvalues 5, 5, 5, then multiplicity of that particular eigenvalue is 3. Similarly, you can have various multiplicities for the various eigenvalues. So, on the x axis you plot the eigenvalues, and on the y axis you plot their corresponding multiplicity, then you get the spectrum of the graph. It will be very clear with an example. We will start with a very simple example. So, I have a triangle, say a very simple graph. Okay. So, now let me ask you, find out the eigenvalues and eigenvectors of this graph. Let us try it. So, what is the adjacency matrix? Right. So, this is the adjacency matrix of this graph. Now, you want to find the eigenvalues of this graph. How do you go about it? So, you set the determinant of this to 0 and you try to solve this equation. If you understand this step, so this comes from the very basic equation of eigenvalues, which is A x is equal to lambda x. From this, all the eigenvalues lambda satisfies this particular equation, which is called the characteristic equation. So, what would be the characteristic equation in this case? So, we have 0 minus lambda 1 1 . This bar stand for determinant. So, this determinant should be equal to 0. Now, let us do some very simple maths and try to expand it. So, it is minus lambda square minus 1. So, please try to follow me. If at any point you are not with me, please stop me. So, I have this minus lambda, I am multiplying this lambda square, and I am multiplying these two and subtracting this. This is the first. Then I have this one minus 1 times this is minus lambda minus 1 and plus 1 times this, which is 1 minus lambda, which is plus lambda. Okay. So, if I simplify, I have this plus lambda plus 1 plus lambda, or I have 3 lambda plus 2 minus lambda cube equal to 0. So, this is the equation that we get finally. So, now you want to solve this equation. See what are the solutions of this equation. So, if you try to factorize it, actually let me tell you, one of this factor is lambda minus 2. We will see that. So, if one of the factor is lambda minus 2, you can just revert the signs. So, it will be like lambda cube minus 2 minus 3 lambda, right, equal to 0. So, the other factor is lambda square. So, that gives minus 2 lambda. So, and you have minus 2 lambda square here. Did I miss anything? Yeah, that is okay. Yep. So, you have 1 lambda minus 2 as a factor. If you factor out, you have lambda square
plus 2 lambda plus 1,
and you have plus 2 lambda, which will give this lambda square, which will cancel this one, plus 1. equal to 0, which is okay. So, then what are the eigenvalues? 2, -1 and -1. So, lambda 1 is equal to 2, lambda 2 is equal to -1 and lambda 3 is equal to -1. So, this is the principal eigenvalue, the others are the other non-principal eigenvalues which are -1 and -1. So, then what is the multiplicity of this eigenvalue 2? It is 1, and what is the multiplicity of this eigenvalue -1? It is 2. So, now if you plot the spectrum, it will look something like this. Actually, for this graph it is very simple. So, suppose this is 0, this is 2, this is -1. So, at 2 you have 1 and at 1 you have 2. So, this graph is actually the spectrum, but for very large graphs you will have a large number of eigenvalues. It is not only a -1 and 2, you will have the all eigenvalues and you will get a nice looking curve. We will see examples very soon. So, if your graph has billions of nodes or say even millions of nodes, it will have millions of eigenvalues and then you will get a nice shape. But before we go to that, let us also do a little exercise and try to find out the corresponding eigenvectors for this matrix that we worked out now. So, here is the matrix, right, here is A and here is x, the eigenvector we want to find, and this is equal to, say we are trying to find the principal eigenvector. So, 2 times x. So, do you know how to solve this equation? This is a set of linear equation, right. So, what happens is you can write x as x1, x2 and x3, and so if this is A, you can write it as x1, x2, x3, and now if you expand these equations, what you get, x2 plus x3 is equal to 2x1 and then x1 plus x3 is equal to 2x2 and x2 plus x3 x1 plus x2 is equal to 2x3, and this is a system of linear equation which you now try to solve, and but actually you can't solve it exactly because there is not one single eigenvector. You can multiply it. So, you have to fix one of them and solve for the rest. So, say we assume that x1, there are many methods of doing so, you can get the ratios and then solve it, or we can do it alternatively. Let us assume that say x1 is equal to 1 and then try to solve the rest of the equations, and you can try to do it. And what it will turn out is x1 is equal to x2 is equal to x3 is equal to 1. You can see that very clearly, right, it satisfies this equation. So, the principal eigenvector in this case is 1 1 1. Now, before we move on to the other eigenvectors, let me ask you this. So, we said that the principal eigenvector corresponds to the popularity sort of. Does it make sense in a triangle that all nodes should have the same popularity? It is exactly right, because all the nodes are isomorphic here. They all, so you have 3 nodes here and there is no reason to prefer one over the other. So, that is why naturally they get the same eigenvector component. Even yesterday we saw that while computing the page rank. But there is also another very interesting thing. Since there are nodes which are isomorphic, they look exactly the same, this eigenvector -1, sorry, this eigenvalue, particular eigenvalue -1 is being repeated here. So, we will try it in the next problem to understand it clearly. So, here we did it for triangle. Can you generalize it for an n-click? You have the eigenvector is 1 n times, right. So, the click is like all zeros in the diagonal and rest are all ones. Okay. Rest are all 1. So, if you multiply it by the all 1 vector, what do you get? What is this value? N minus 1, n minus 1 and n minus 1, right, and which is actually n minus 1 times all ones vector. So, what is the eigenvalue here? N minus 1. So, now you saw why in triangle it was 2. So, it is 3 minus 1 which is 2. So, for a clique with n nodes, the biggest eigenvalue is n minus 1. What about the other eigenvalues? Actually, if you try to solve it, you will find all the other eigenvalues are minus 1, like in the earlier case. So, now if you draw this graph, actually here at n minus 1 and here will be minus 1, this is 0. So, here is a small peak here and there are n minus 1 nodes. So, sorry, this eigenvalue minus 1 has a multiplicity of n minus 1. So, the spectrum looks like this in this case. Okay. So, here also you saw that since there were n nodes each resembling the other. So, you can think of one node being standing there and rest of the other n minus 1 nodes are just copy of that node. So, therefore, this eigenvalue minus 1 is repeated n minus 1 times, and for this one node which is a standalone node, for this you get a eigenvalue which is n minus 1 in this case. And again you should not prefer anybody. So, naturally the first eigenvector is the all ones vector. You can now try out the other eigenvectors. I will not spend much time solving it, but let me tell you, or they will look like this. So, one of the entries will be 1, the other entry will be minus 1 and rest will be 0, and you can actually clearly see how it will work actually. So, you can just do the calculations and you can see that if you do this, if you take A and multiply with this, the corresponding vector you will get is this actually. And there is also a very interesting property. We can, if you want, we can work it out for the case of the triangle. It's like it will be very simple. Let's just do it. So, let me multiply it by this vector. So, what is this row? So, it is 0 minus 1 0, and what is this? This is 1 0 0, and this is 1 minus 1 which is 0. So, it saw this. So, it is minus 1 times 1 minus 1 0. Okay. So, this is the other eigenvector. And you can see one very interesting phenomenon going out here. So, this was the first eigenvector and this is the second eigenvector. What is the dot product of them? It is 0, right. What it means that the second eigenvector is perpendicular or orthogonal to the first eigenvector. Actually, this is also a very general property for the adjacency matrices of graphs. The second eigenvector will be orthogonal to the first eigenvector. So, these are some properties which we will use later on in dealing with large graphs, proving interesting properties about them. To further understand what is really going on, how eigenvectors and eigenvalues work, you can also try to find out the eigenvalues of a complete bipartite graph. So, what happens in a complete bipartite graph? Say I take a small one. This, right. So, what will be the adjacency matrix for this graph? So, for your benefit, let me write it this way. Right. So, this is how it looks like, and now suppose you are asked to compute the eigenvector or eigenvalues of this graph. So, I will not go through this whole computation again, because now we will have 5 eigenvalues, but can you just guess, you know, which of the eigenvalues, how many eigenvalues are going to be repeated this time?
One eigenvalue will be repeated thrice and another one two times.
You are on the right track, but not exactly. So, this is a copy and this is a copy of this one. So, one eigenvalue will be repeated twice, the other is actually only once. So, it is not sort of a repeating, but there will be 2 distinct eigenvalues for these 2. So, if there is a multiplicity of eigenvalue, one particular eigenvalue repeats many times, it has a clear indication of how the graph would look like. There will be nodes which will be structurally similar to each other. We will see more on this later on. So, as I said, if you have very large graph, you will see very nice, you know, looking curves rather than, you know, all the eigenvalues at -1 and 1 at n minus 1 and so on. So, here are some examples. I have taken it from a paper by Banerjee and Yost. So, all these experiments were on the graph Laplacian, but do not worry at all, just look at the shape, because even if you had done it on the adjacency matrix, the shape would not have changed much, but the scale would have changed. If you notice, actually in the case of graph Laplacian, the eigenvalues always lie between 0 and 2. So, you can prove it actually. So, that is why, you know, the spectrum always lies between, this is 0, this is 2, I do not know if you can see. So, it always lies between 0 and 2, but forget about it, just concentrate on the shape. So, this first one is for Erdos-Renyi graph. So, are you familiar with Erdos-Renyi graphs? You do not know. So, Erdos-Renyi graph is, suppose you have a, it is a most simple random graph model. So, you have n nodes. How many edges are possible? Suppose you have an undirected graph. So, how many edges are possible? Right, n into n minus 1 by 2 edges are possible. And you say that there is a probability p of having an edge. So, basically if I say the probability of having an edge is 0.5, so you will add n into n minus 1 by 4 edges, and those 4 edges you just add randomly. You do not look at anything, just randomly pick 2 vertices and add an edge. So, in such a graph, so this is actually equivalent to what is called a random matrix. So, what happens in a random Boolean matrix is you take a matrix, put all the diagonal entries to be 0. For all the other entries, with a probability p, you make a 0 to 1 and do it for every cell independently of what you did for the other cell. Actually, that will be the adjacency matrix for an Erdos-Renyi graph. Is it clear? Like that will be non-symmetric. So, you do it for the upper triangle and you have to do it, repeat it for the lower part to make it symmetric. So, that is how you get the adjacency matrix. So, for such matrices, the spectrum looks like this. Actually, this is slightly stretched because the scales on the 2 sides are not similar and it is Laplacian. But if you draw it for the adjacency graphs, you would see actually a very nice semicircle. So, suppose this is the eigenvalues. So, you see a nice semicircle actually. The multiplicities are such that they lie on a semicircle, this curve, and this is a very famous law. It is called Wigner's semicircle law. So, but the proof is involved and I am not going into the proof. You might look it up for yourself. So, it is called Wigner's semicircle law. The other 2 are for some other models. Again, those models have not been covered in the course yet. So, I will not go into the details. So, first is a small world network. You can think of the social network of friends. If you calculate the eigenvalues and eigenvectors, it looks like this. So, something like this, and here is an interesting network. It's a power law network, and here you see a peak at 1. Actually, a peak at 1 for the Laplacian actually means a peak at 0 for the adjacency matrix. So, having a large number of 0 eigenvalues is itself very interesting. Again, we will see what it means. But before we do that, let us try to get some alternative interpretation of eigenvalues and eigenvectors, because that is necessary. Till now we are trying to solve examples and try to get a feel of what these eigenvalues and eigenvectors would mean. but in general what an eigenvalue or eigenvector would mean for a graph or in general for a matrix. Let us see. Yes.
How do we calculate eigenvalues of very large graphs? Do we do the same thing?
That's a very good question actually. The question is how do we compute eigenvalues and eigenvectors for very large graphs. You cannot compute it exactly as I did for the small graph using some algebraic technique. So, necessarily what you use is some numerical technique. So, there are methods, very fast numerical algorithms. There are methods which are implemented in MATLAB. You have functions which you can call on large matrices and it will automatically give you the eigenvalues and eigenvectors numerically. So, you will not get the exact value, but still those methods work for graphs of the size of say 10,000 nodes of that order. If you go beyond that, actually even those techniques fail. So, you have to find out better techniques. So, there are approximation algorithms for doing that. So, you do not sample, look at the whole matrix, you sample parts of the matrix and based on your idea about the sample, you try to generalize. So, you just get a vague idea of how the spectrum would look like or some of the eigenvectors would look like, but you do not get all the eigenvalues and all the eigenvectors. So, for example, if you want to do it for the web, it is a huge graph, billions of nodes. So, you can't really do any of these techniques.
But the numerical algorithm, perhaps it's the power iteration method.
Yeah. So, the remember the hoteling algorithm that I talk about yesterday, remember that? So, if you have this equation, right, x gets ax, say x1 gets ax0 and you continue this equation, then ultimately you get something like this, and does not matter from where you start, where you end is the eigenvector, the principal eigenvector. That is what I told you in the last class. So, you can use this power iteration method, you can find out each of these eigenvectors and remove them and then do the computation and find the next one. So, there are many numerical algorithms. Yeah. So, coming to alternative representations. So, a matrix can be also viewed as a set of linear equations. So, if you have a matrix like Ax equal to some b, x is a vector, v is a vector. So, what you are essentially talking of is a set of linear equation, right. So, it is more clear if I expand it. Then I am saying something like this, right. So, these are a set of linear equations, and if you solve for x, basically you solve this set of linear equations. In that context, what are A and C then? What are this matrix, what it is representing basically? So, if I ask that question, so why these equations are called linear equations, in other words? Why what would be a nonlinear equation, or can you tell me that? So, it has all power 1 of x, right? There is no power second or higher power of the, but why it is called linear? The linear word comes from line, right? Does that does this have something to do with lines? Right. So, if you plot in 2 dimension, these will be lines, right? So, x1 plus x2 will represent something like this, and the other will represent this, and this system is solved for this particular point. In general, if it is an n dimensional, A is an n cross n matrix, then what would this represent? Still there will be linear equations, but in this case they will not be lines, they will be planes. Yeah. So, there will be planes on n dimension, so hyperplanes, and this matrix then essentially represents a set of planes. These coefficients, these rows actually are representing a set of planes, of course with B. So, sometime you might assume that B, people sometimes do this, that B is set to 0, and then they represent a particular kind of planes, a family of planes. Now, the question is whether we can, so that is one interpretation. So, all the rows essentially represent a line, the row vectors are basically representation of some line or some plane in the geometric space. And if that is so, can you tell from some very basic you know, your algebra ideas that when such a system is solvable, when there exists a single solution, unique solution, and when doesn't exist? If there is non-vanishing, I can't hear you. Yeah. So the best way to see it, like the way I see it geometrically, if the lines are parallel, there is no point of intersection. Or if the lines are coincident, they intersect at every point, there are infinite solutions. Anyway, so if we take the case that the two lines are parallel, what essentially would mean between A, C and B and D? A by C is B by D, or rather a better way to write it may be A by B is equal to C by D. Yeah. So what it means is this row is nothing but a multiple of the other row. So this row can be expressed as, you know, the combination of the, you know, as a multiple of other row. In case of many rows, say it's 2, in case of say 3, the solution might not exist if it need not be like that the 3 planes are parallel. It suffices that one of the planes can be written as combination of the 2 other planes. Even then this system is not solvable. So such a system is called linearly dependent system. So basically one of the rows is linearly dependent on the other rows. You can express it as a linear combination. So this is also an important concept, it's called that of linear dependence. And if all the rows are not linearly independent for an n cross n matrix, then it is not invertible. Because if the matrix is invertible, then actually, you know, it's very easy to solve such an equation. So remember, you have Ax equal to b, and you could just do x equal to A inverse b. So if A inverse exists, you could always solve for x, but in such cases A inverse does not exist. So the matrix is not invertible. So there are certain repercussions of this on the eigenvalues. If the matrix is not invertible, it has to, you know, the eigenvalues have certain properties. Can you guess what kind of properties it will have? Okay, we will see maybe just after a few slides. Come up again. How many? So one of your friends says that eigenvalue will be 0 or eigenvalues will be 0. So I just asked how many of them needs to be 0, and actually the answer turns out that to be correct, he is right, that even if one eigenvalue of the matrix is 0, it is not invertible, and we will prove that why this is so. We will see examples actually for why this is so. Alternatively, if a matrix has a 0 eigenvalue, it means there are rows which can be written as linear combinations of other rows. Also, another way to look at it is matrix as an arrangement of column vectors. So you have A, and instead of writing A1, A2 and A3, you could think of, you know, it as a vector. Each of them is a vector, right? Each of them is a column vector. And actually when you do now Ax, where x is x1, x2, x3, basically you are multiplying v1 with x1, x2, sorry, v2 dot dot dot, and this is giving you another vector. So x is a sort of a weight vector, you are multiplying each of these vectors with these values to get the final vector b. So what combination of these vectors give you b? So this is the question. And if x1 and x2 are parallel, sorry, v1 and v2 are parallel now, then you can get this vector b by some combination of them if and only if b is also parallel to them. And in that case, a large number of combinations can give rise to b. Otherwise, you will not get any other combination, right? So if this is suppose b, and this is say v1, this is say v2, and this is say b dash, b prime. So you can get this b because it is parallel, and any combination will give this b. On the other hand, this is not parallel. In that case, if v1 and v2 are parallel, no combination of them will give this. So this is the situation when it, you know, as I said, for parallel lines you have no solution, is the singular case, whereas this is the case when it has infinitely many solutions. But the best case, means the nicest case, is when V1 and V2 are not parallel. So, if V1 is in this direction and V2 is in this direction, any point in this space can be represented as a combination of V1 and V2. So, they form a what is called a basis for this space. So, you must have studied all these in your linear algebra course, but I am repeating some of them because we will use some of them later on. So, now let us come to some of the very interesting properties of eigenvalues and eigenvectors. Some of these properties are also very important for complex networks, some of them are in general interesting. So, let me ask you this question, it is actually a very simple question. Suppose I have a diagonal matrix. A diagonal matrix means all the non-diagonal elements are 0 and there will be values only on the diagonal, non-zero values. What will be its eigenvalues? Right. So, the values in the diagonal will be the eigenvalues, and what will be the eigenvectors? Right. So, the one of the eigenvector will be 1 and followed by all zeros, the next one will be 0, 1 followed by all zeros, and so on. You see an interesting thing, that all these eigenvectors are orthogonal to each other. You will have n eigenvectors and all of them will be orthogonal to each other. What happens for a triangular matrix? So, you know what is a triangular matrix? So, in triangular matrix, one side of the diagonal is all 0 and positive entries, sorry, non-zero entries are here on the other side. It can be upper triangular or lower triangular, the alternative case is also possible. So, these are like x1, x2 and so on. You could also think that here you have non-zero entries and here 0. So, what will happen for triangular matrices, the eigenvalues and eigenvectors? Take a simple case, 1, 2, 3, 0. What are the eigenvalues of this matrix? 1 and 2. Do you know why? Can you see why? Exactly. So, when you do the determinant, the characteristic equation, you have actually the characteristic equation turns out to be this, right? Because rest of the terms gets multiplied by 0 and gets cancelled out. So, only the diagonal remains. So, one eigenvalue is 1 and another eigenvalue is 2. So, for a upper triangular or lower triangular matrix, the eigenvalues all reside on the diagonal. This is also a very nice property. So, even if you have a very large matrix, if it is a diagonalized matrix, sorry, it is a triangular matrix, it is so easy to get its eigenvalues and eigenvectors. Also, what about the eigenvalues and eigenvectors of A transpose? Does it have any relationship with A? So, what happens if A is a symmetric matrix? What about the eigenvalues and eigenvectors of A? It will be same, not 1, it will be same, because for a symmetric matrix A is equal to A transpose. But I am asking for a general matrix. What happens for a general matrix? The eigenvalues and eigenvectors of A and transpose? Values don't change? Do you know it or? Right. So, the eigenvalues and eigenvectors remain, the eigenvalues remain same because the determinant does not change. You can see it in this way. So, this is the characteristic equation for the eigenvalues of A, okay. And for A transpose, this is the characteristic equation, which is actually also right, because this lambda I is the identity matrix. So, for the identity matrix the transpose is the same. So, it is A minus lambda I the whole transpose you can do. Are you with me on this particular step? Because lambda is affecting only the diagonal and rest of the things are permuting from the rows becoming column and the column becoming rows. So, this is the characteristic equation. Now, for determinants, you know that the characteristic equation of the transpose is same as that of the original determinant, and that is why you know, that eigenvalues of the transpose matrix and the original matrix are the same. But what about the eigenvectors? Okay. Okay, so it's not clear actually whether eigenvectors will also be same or not. So you can see with a few examples, work out a few examples to see that actually eigenvectors are not same. And what exactly are the eigenvectors depends on lot of issues, like it's not a very simple transformation by which you can get the eigenvectors, but the eigenvalues are the same. Now here is again a small problem for you. So now having known all these facts, can you prove that a Markov matrix will always have an eigenvalue 1? So you remember the property of Markov matrices? All the elements are positive and each row or say each column sums to 1. So now can you tell me that it will always have an eigenvalue which is 1? Can you prove that? Right, and
For that vector, you can directly see that one is an eigenvalue.
right. So if your Markov matrix is a row matrix, then you are done. It's very easy. See, and so on. So what happens if it's a row vector? Then sum of all these row stochastic matrix, then sum of all these rows is 1. So all these sums are 1, and now you multiply it by this all 1 vector. What do you get? This plus this plus this is 1, and this plus, so again you get 1 1 1 1. So this is the eigenvector and the corresponding eigenvalue is 1. On the other hand, if it was a column stochastic matrix, so if you added it this way, it would have become 1, but not this way. In that case, you would have just done a transpose and said the transpose has the eigenvalue 1. So we know by the previous theorem that the original matrix also has eigenvalue 1. So that is why all Markov matrices or stochastic matrices will have eigenvalue 1, which we used last day to, you know, show that the page rank would eventually converge. Yeah, here are some more interesting properties of eigenvalues. So what it says, this theorem, it says that the trace of a matrix is sum of the eigenvalues. So you know what a trace of a matrix is? Sum of the diagonal elements. So what it says is the trace of a matrix is sum of the eigenvalues. So what we will do is we will just take a very small example and show it. We will not prove the general case, but I will give you the sketches of the proof. So this is suppose your matrix. So sorry, then in this case the characteristic equation would be this, which is lambda square minus this. So this equation has two roots, lambda 1 and lambda 2, and what is the sum of the roots? A plus d is the negative coefficient of the lambda. It's a very simple fact about the quadratic equations. So in this way you can prove for the quadratic case, you can prove it actually for the general case. You can show that, you know, even for an n cross n matrix, the sum of the diagonal entries actually is equal to the sum of the eigen values. Now till now we have solved many matrices, right? Cliques, bipartite networks, and for all of them we try to compute the eigenvalues. So just quickly think about it, that whether this property is satisfied for all of them. So what is the trace of all these adjacency matrices? 0, because we are not considering self loops. So then sum of the eigenvalues should be 0. Was it true? It was, right? So for a clique, the one eigenvalue was n minus 1, rest of the n minus 1 eigenvalues were minus 1. So the total sum is 0. So it is true for actually any matrix, and it is a very interesting and useful property. Another thing which is really useful is called diagonalization of matrices. So, think here S is basically, suppose x1, x2, xn are the n eigenvectors of this particular matrix A. So, these are the eigenvectors of this matrix A. Then S is this particular matrix. So, if this is the case, and lambda is this actually, lambda is a diagonal matrix where the diagonal elements are the and rest all are 0. So, can you show that this holds? This is also again very straightforward. What is AS? So, you have A times x1, x2, xn. So, you know A times x1 is and so on. Right. On the other hand, if you do this, what is S lambda? Xn times lambda 1, lambda 2 dot dot dot. It will be again lambda 1 x1 and so on. Right. So, now you can see that AS is equal to S lambda and multiply by the inverse on both the sides and you get the theorem. Okay. So, this is a very important property. Why this is very important? Because you can use this to now find out what are the eigenvalues of A square or what are the eigenvalues of this matrix A power k. Tell me. Suppose the eigenvalues of A are lambda 1, lambda 2 and up to lambda n. Then what is the eigenvalues of A power k? Can everyone see this, that these eigenvalues will be lambda 1 power k, lambda 2 power k up to lambda n power k? So, actually you can use this particular theorem. You just multiply it twice and here you get S inverse gives you I, the identity matrix, or A square S equal to lambda square. So, you see A square has the same eigenvector as A, they are stored in S and the eigenvalues are lambda 1 square, lambda 2 square and so on. And similarly A power k has the same eigenvalues as A and the other things that is the eigenvalues are lambda 1 power k to lambda n power k. But one important thing here is if A and B are two matrices and if you multiply A and B, will AB also have the same eigenvalues as A and B? So, say if A has eigenvalues lambda 1 to lambda n and B has eigenvalues mu 1 to mu n. So, will the eigenvalues be lambda 1 into mu 1 and lambda 2 into mu 2 and so on? No. Under which condition they will? Right. So, if the eigenvectors of the two matrices are identical, then this will hold. Otherwise, in general it does not hold for two matrices A and B.
Will S always be invertible?
Yes. So, actually you can prove that S is always invertible. The eigenvectors are all linearly independent. So, therefore, S is invertible. Actually, we already saw that the second eigenvector is orthogonal to the first one. Actually, all of them are orthogonal to first one and all of them are also linearly independent from each other. But actually, there will be matrices which may not be diagonalizable also. So, there are actually certain matrices which are not diagonalizable. Very few cases, they are called defective cases. I think I have one example. I think this you just try this out. I think this particular matrix is not diagonalizable. Okay. Coming to the last of the interesting properties, it's called Frobenius norm of symmetric matrices. So what's a Frobenius norm of a matrix, or rather what's a Frobenius norm of a vector? Do you know? Have you heard of Frobenius norm? Have you heard of L2 norm? So what's that? Yeah. So for a vector, it's very simple. The norm is something like, if V is a vector, it's like V1 square plus V2 square Vn square root. Okay. This is the Frobenius norm of a vector. So similarly, Frobenius norm of a matrix is you take all the elements of the matrix, square them and add them. This is called the Frobenius norm of the matrix. Can you show now that the Frobenius norm of the matrix is equal to the sum of the squares of the eigenvalues for a symmetric matrix? Okay, let's see. Suppose A is a symmetric matrix, then A is same as A transpose. Okay, forget about A being symmetric. Think of A transpose. What are the diagonal elements of A transpose? What will be this element? This is plus and so on. What will be this? Right? Can you see this? If you take a small matrix, it will be very clear actually. A1, A2, A3, A4, and I take its transpose A1, A3, A2, A4 and multiply it. Then this is A1 square plus A2 square, and this particular thing is A3 square plus A4 square. So what will be the trace of this matrix? A transpose, trace of A transpose, which is the Frobenius norm square. So I did just a small mistake. It's the sum of the eigenvalues, square of eigenvalues, and square root of that, or essentially the square of the sum of the all values is same as the square of the sum of the eigenvalues. Sorry, sum of the square of the eigenvalues. Okay. So this trace of this matrix A transpose is same as the Frobenius norm square. And now if A and A transpose are A is symmetric, then A and A transpose are same. So it's the trace of A square. And you know that this is actually, so each of the eigenvalues is the square. We saw it previously, right? So A square, the eigenvalues of A square are lambda 1 square, lambda 2 square, and we know that the trace of A square will be equal to the sum of the square of the eigenvalues. So which is this? So this shows that the Frobenius norm, the square of the Frobenius norm of the matrix is equal to the sum of the squares of the eigenvalues. So you got two very important properties for estimating what will be the eigenvalue, the spectrum looking like. So if you take the square of all the eigenvalues, it should be the square of all the values, sum of the square of all the values in the matrix. So if the values in the matrix are small, then this cannot be large, the eigenvalues cannot be large, for instance, because I am talking of real eigenvalues, I am talking of matrices which are representations of graphs. Okay. So next we will see some real examples and case studies of spectral analysis of networks, how really the first eigenvector or the first eigenvalue, what it really means for different kinds of real world networks.